is preparing to live stream. Okay, great. And I'm going to close that window because I don't want to see that. All right.
It's showing up on the YouTube channel, so I think we're ready to go start the webinar, right?
Okay.
But make Tim host.
I think John will set up the spotlighting, and then Tim can reclaim host automatically.
Oh, okay.
And those of us that don't want to appear on camera should mute their camera and audio, right?
And currently I see several people spotlighted. I know we're on live. Welcome everybody, but we're going to take a couple minutes here to get ready. Okay, I think the spotlighting's set up right now. Although there's 2 interpreters on screen right now. Okay.
Did you already start the webinar, John? Because I still see the start webinar button at top.
I did not start the webinar because I'm no longer host.
But, oh, I see.
I think we are broadcasting because I can see people. You're going to wait a moment here.
John, at this moment, you are host, and it looks like only one ASL interpreter is spotlighted. So we'll just need to spotlight John and Florian as well.
I'm not host.
You are.
Oh, I shouldn't be.
And I don't know, Chris, if you see it, but I still see the start webinar button. So I think that's
I figured we would
live
just,
yet.
I can add these spotlights as co-host, actually. I'll spotlight John, Florian.
Oh, I thought that you were going to be host, Chris, but you're supposed to be setting, and am I doing the show start webinar? I see, I am. It hasn't started yet. Okay.
Yeah, we should start, right?
We were safe to start.
Okay, I'm going to hit start webinar then. Okay, hi everybody. I'm going to wait a moment to let people join. So we'll just wait for a minute here. Okay, great. I'm going to get started here. Hi, everybody. I'm John Trueswell. Welcome to the 34th Annual Conference on Human Sentence Processing. I'm the chair of the Conference Organizing Committee this year. And so here we are again, joining virtually, unfortunately. I wish we could all be in person. Hopefully that will happen at next year's conference. So just a few things to say at the beginning here. As many of you know, the CUNY conference was established by Janet Fodor and her colleagues at the Linguistics Graduate School in the University of New York. And over the past 34 years, the conference has brought together those interested in understanding how humans comprehend and produce sentences, both in written form and spoken form. And it has long been an interdisciplinary gathering, bringing together linguists, computer scientists, psychologists, and many more people. And it really was Janet's vision that this would be an interdisciplinary Cognitive Science Conference, and it has truly been a great success. This morning, the first thing that I want to do is to welcome everybody to Philadelphia. I wish you guys were here. It is a spring day here, sort of. Things are starting to melt from our terrific snowstorm a while ago. Also, welcome to Penn's campus. I'm not even on Penn's campus, but I am here in Philadelphia. And again, I wish you guys were here to be able to walk around and see our wonderful campus. And in addition, I want to give a hello, shout a hello from everybody in Penn's language community. Penn is a terrific place, as you know, for psycholinguistics, computational linguistics, formal linguistics. A really great group of people are here, many of whom are joining today, and a number of them were on the organizing committee to help make this conference begin and hopefully be a big success. So welcome everybody. A few things left to do in the announcements here, in the opening remarks here. Here's what I'm going to try to do in the remaining few minutes before we get going. First, I'm going to introduce the special session theme, and then I'm going to do the announcement for the Katz Award, the student award for last year's conference. It's the tradition to announce last year's winner at the start of this year's conference. And then we'll have an announcement about the CUNY conference from Jennifer Arnold, who will be joining us. That's about the ballot that many of you have seen going around in the email. And then I'm going to spend a few minutes trying to explain how the whole Zoom webinar thing is going to work. Okay. So first, it's a great pleasure to announce the special session topic for this year's conference. We decided on the topic of language acquisition and language processing, finding new connections. This is funded by the National Science Foundation, the special session theme, which includes these terrific invited speakers, but also a number of regular talks that are on this same theme. So as many of you know, the two largest subfields of psycholinguistics today are language acquisition and language processing. And in many ways here, at least here in the US, the two big conferences that are connected to that are BU, the BU conference. I don't know why it forwarded on me like that, but sorry. The BU conference, but also the CUNY sentence processing conference, one on acquisition and one on processing. And the field actually has traditionally taken a divide and conquer approach to the topics of acquisition and processing. But really in the last 20 years, this artificial divide has been blurring. Both at BU, we see lots of language processing talks. Acquisition researchers are now using a variety of methods to examine how infants and toddlers interpret speech and sentences in real time, asking how they take newly learned knowledge about the language and apply it on the fly as speech is unfolding, since that's what they have to do. In fact, it's really quite enlightening to do these online measures with children, because you realize that the input that they are getting has to go through some kind of real-time processing device. So the information that they're gathering about the language is going through a processing system. And then likewise in adult psycholinguistics here at CUNY and lots of other conferences, we've seen a great deal of interest in the last 20 years for artificial language learning experiments, conducted sometimes on individuals, sometimes with groups of subjects, and even sometimes between groups transmitting language from one artificial generation to the next. And this has been a really exciting time, because this sort of experimentation, I think, has really led to people developing theories that attempt to unify acquisition and process. And we have a terrific set of invited speakers lined up that I think exemplify this approach. Anne Christophe is going to be presenting, Cindy Fisher, Jeff Litz, Chris Manning, Alyssa Newport, who will be presenting this morning, and Linda Smith. So these are all really exceptional researchers that have been transforming this field of acquisition and process as one research topic. And in addition, as I said, there are a number of presentations, regular presentations that were selected as part of the special theme. If you go to the conference website and look at the schedule, you'll see which ones are marked as that with a little star next to them in the schedule. Okay, so that's the special theme. The next thing that I want to do, which is always a lot of fun, is to announce the next winner of the Katz Award. And for some reason, I can't get my slides to advance at the moment. It's not cooperating. There we go, finally. All right, so each year we announce the Katz Student Award, and it's in memory of our friend and distinguished colleague, Gerald Katz. And this is the Young Scholar Award. It's awarded for the paper or poster presented at the annual CUNY Conference on Human Sentence Processing, best exemplifying the qualities of intellectual rigor, creativity, and independence of thought, which characterized Dr. Katz's life and work. And this year's winner from last year's conference, we announced it this year, the winner of last year's conference, so at 2020. The recipient is Maryu Katz, who was a student at University of California, Los Angeles. And congratulations to Maryu. And hopefully she's here as one of the attendees. So let's all just applaud her. The award recognizes the excellence of her paper entitled Processing Coordination, Ambiguity, and Context, Eye Tracking Evidence from Estonian. The paper was presented virtually at the 33rd Annual CUNY Conference on Human Sentence Processing, hosted by the University of Massachusetts Amherst. With her doctoral degree completed in December 2020, Dr. Katz has taken up a lectureship at Birkbeck College at University of London. So congratulations to her for all of that. Okay. All right. That is the award. And now what we're going to do is we're going to do a short announcement about the CUNY ballot that you've been seeing sent around. What I'm going to do right now is switch over to Jennifer Arnold, who is going to hopefully be spotlighted now. She's going to make a short announcement about the CUNY ballot. Jennifer, I think you are on.
All right. Hello. Thanks, John. And good morning, everybody. And so as you probably know, there are two issues that are facing this conference. And one is a proposal that's been floating around for several years now to form a non-legal society, which is essentially going to consist of an organizing body that would help facilitate the conference. And the other is the issue of changing our name. Now, we all have very positive associations with the name CUNY Conference. I know I do. I've been coming here for over 25 years. But it also can pose a problem for organizers at other universities. And so this raises the question of what the new name should be. And so we've had several committees debating these issues for the last 3 years since the Davis CUNY. And it's now time to get the input of everybody else in the community, so all of you. That's why we're, that's why we're doing this vote. And so I'm sorry for spamming you with all this email for the last few days, but we really want to make sure we get widespread participation, get everybody involved. So if you are a regular participant in CUNY, so unfortunately, sorry, this doesn't include people who are here right now for the very first time, but if you're a regular participant, you're eligible to request a ballot. And so this is a two-step process because the ballots then need to be sent out manually. And I'm very grateful to Mirren Edelstein, who is a staff member at UCSD in Vic Ferrera's department. And so the deadline, or the original deadline, passed, but we've extended both the deadline to request a ballot and the deadline to actually vote. But this is going to need, we're at the very tail end of this, so it has to happen very quickly. So right now, after I finish this chat, this announcement, I'm going to put a link in the chat, and you can click on that link to request your ballot. And then I will send these names to Mirren after 11 o'clock Eastern time this morning. She'll hopefully get those out this afternoon, and we're extending the voting window until 9 a.m. tomorrow morning. Okay, so this is your very last chance to participate, and then at 9 a.m. tomorrow morning, we're really going to stop it. This is also the last announcement you'll get from me until we announce the results on Saturday at the start of the last session.
Yeah, the last. I was just
yeah,
going to say at the start of the last session, Jennifer will be the session chair, and she's going to make the announcement then.
Yeah, and also I'm going to put my email in the chat. If you have any questions about this, send me an email.
Okay, great. Thank you, Jennifer. That's great. Okay, we of course are already starting to run a little late here. We began a little bit late. So I just want to make sure that everybody has a good understanding of how all this is going to work. I hope. I hope it will work this way. A couple of things to know. First of all, we've set up two ways to join and participate in the conference. One is through the CUNY 2021 website. You've been getting emails about that. Our apologies to people whose spam filters and other things have made it difficult for you to get an account on that website. But you know, if you have an account, you can access the website, which has all the links for the Zoom webinar, for joining the Zoom webinar, etc. For everybody, including those that have accounts and those that don't have accounts, if you've been registered through the registration form that was a Google form, if you've registered, you're going to be getting a daily morning email, and you should have gotten one this morning. I hope that you did. It includes the Zoom webinar link, which is a single webinar link that works for all of the main sessions. Okay, and in addition, there are a set of links for the individual Zoom sessions for the parallel talks, and that should be there. So let me just briefly now, so that's how you would join either way. If you get the email, you don't have to log in to the CUNY website. You can just simply click on the links in the email, and hopefully that will all work well. Okay, so very briefly here, how the plenary sessions are going to work, the main plenary sessions are going to work. They're going to work very much like last year, Zoom webinar. We can't see you or hear you, so relax and enjoy. And you should, if you can take a moment to set your Zoom webinar name when you join in the following kind of format. You can do this a little later by logging out and logging back in when it asks for your name. Hopefully you'll put your first and last name, and then in parentheses your affiliation and whether you're a student or a postdoc or a faculty. Yeah, my slides keep advancing. So how you're going to ask questions is very much like last year. You're going to click on the Q&A button in the Zoom tray, usually at the bottom of your screen, and it'll ask you to type in your question. That will go only to the session chair, not to everybody, so no one else is going to see your question that you type in. You can do that during the talk, toward the end of the talk. They'll populate the question Q&A for the session chair to see. Then the session chair is going to, during the Q&A, pick a question, and that will either either what you can do, two different things can happen. We can unmute the questioner who can ask the question live, or the session chair can ask the question for you. If you do that, just please indicate that in your question. Maybe just say, please read Q for me, or something like that at the beginning. We will hopefully try to have the first question go to a student or postdoc. We want to try to encourage students and postdocs asking questions. And so that's why you should try to put your, whether you're a student or postdoc, in your name, because that's the only way we'll be able to know. Okay, so now, in addition, so that's how these sessions will work. Parallel sessions include Zoom sessions, individual ones. The links are provided in the daily email or on the conference website if you log in. Each session is going to be an hour. This is new instead of poster sessions this year. So the first 30 minutes of each of these individual sessions, there will be 4, 5, or 6, it's 5 or 6 presentations during the first half hour, 5 minutes each. And then the remaining time is going to be a Q&A and discussion. We really hope that this is a way for people to talk about the set of talks, the set of presentations together. We've tried to thematically organize the sessions as best we can. Attendees can submit their questions over the Zoom chat in that interface, and during the question and discussion period, the chair will select questions and ask the person to unmute, very much like it works here. Okay, all right. In addition to this, that's an extra slide that says the same thing. Apologies for that. Finally, one last thing. If you want to socialize with people during breaks or anytime really, GatherTown Space is open for you. There's a link on the website for that. There's also a link in the email. We have a cozy living room and also a fabulous rooftop lounge. You can navigate around with your little virtual avatar and talk with people in a Zoom-like interface there. Presenters for each session, we really encourage you to go there after your session during the break, because you can continue your conversation there with people. Okay, and then also a couple of other things, how you can communicate with others, other means to do that. We have Twitter. There's Twitter at CUNY 2021. We have a message board that requires a login on the conference website. And also keep in mind that we have asynchronous discussion with the presenters on the conference website. So in the schedule, if you click on the discussion link next to a particular presentation, you can enter a discussion chat box, which just posts questions, and then presenters can go there and respond to them. Okay. Finally, there is overflow here. If we have too many people attending in the Zoom webinar, that will just simply, that's so that if you, it's unlikely that's going to happen, but also in the email, and we'll put it up on the website. I'm not sure if it's up there yet. You can go to Penn's MindCore channel, YouTube channel, and watch this live stream there. Okay, so I really am now going to finish. Special thanks to everybody, the CUNY organizing committee, all the faculty that have helped with this, the MindCore program manager, Jessica Marcus, who has done all the amazing things for us to get this going. And a special shout out to Penn graduate student Victor Gomez, who helped develop the website, and all of the graduate students and postdocs and alum who are serving as parallel session chairs. They are all a terrific help, and we really are glad that they are able to do that for us. Okay, so I am going to end there, running late, unfortunately, but we're going to now switch over to Florian, who will be the chair for the first session, and we're going to get going here.
Good morning, everyone. Welcome to the first session here at CUNY. I'm Florian Schwartz. I'm here, one of the co-organizers of CUNY at Penn. It's a great pleasure to start out with a wonderful first session where we will have it all, or each, or every. It's all things quantifiers. Let me just make a couple brief reminders just in case people joined right now. We'll make those reminders every time just so everybody stays in the loop. Again, Q&A comes in through the little Q&A button interface in your Zoom tray. You can enter questions there at any point. You're welcome to do that during the talk. I will then select questions from what comes in there during the question period. Please also note that we have closed captions available in addition to the ASL interpretation, which everyone should see. If there's any trouble with that, let us know, ideally through private chat, so we can fix any issues that come up. For the closed caption, just click on live transcript, the little CC button, and select choose subtitles. And like John already said, but again, if people just joined, the discussion pages on the website for each presentation allow you to continue discussion after the Q&A, especially if there are questions we don't get to, those can be handled there. It's now my great pleasure to introduce the first speaker. Timing-wise, since we're running late, just as a heads up, we will obviously give every speaker their full 30-minute time window, 20-minute talks and 10 minutes questions. So we will run a little bit into the break. But without further ado, I'm happy to introduce our first speaker. Tyler Knowlton will present joint work with Justin Halberter, Paul Piotrowski, and Jeff Lids, presenting on evaluating each, but not every, sentences encourages encoding individual properties. Tyler, take it away.
Thanks, Florian. And thanks everybody for coming, welcome. So I want to talk about this new experiment that gets at one aspect of quantifier meanings. But first I want to start with kind of the bigger picture. So at the broadest level, this work is really about what meaning representations look like. So how detailed are they? And how do they connect with non-linguistic conceptual systems? So how are they related to cognition more generally? And as a case study, this talk's going to be about what happens when you process a sentence like every circle is green or each circle is green. I think quantifiers like each and every offer a really good way to get at those kind of broader questions for at least two reasons. One is that we can really state explicit hypotheses about what their meaning representations look like, so we know mathematically how these have to look. And two, we know a lot about the supporting cognitive systems. So we know about numerical cognition and group representation and object representation. And so we're going to use this case, each versus every, as sort of a one case study in looking at these bigger questions about meaning and cognition. And so the local question for this talk will be, how are universal quantifiers like every mentally represented?
Tyler?
Yes, Jeff. Yes?
Thing.
Tyler, your slides are not advancing.
Oh, good. Really? Again? Okay, hold on a sec. Let me see what we can do about that. Okay, how's this?
Black screen.
Really? All right, hold on, give me one sec here. All right, 1 second. Sorry about that, everybody. Okay, so let's try it this way instead. And just share this portion of the screen. How's that look for you?
We can see, yeah, we can see your screen now.
Good.
Okay.
Try advancing it.
How's
Yes,
that
it's
look?
advancing.
It works. I
All
paused
right.
your time. Don't rush. You're
Oh,
good.
it's okay. Sorry about that.
Carry on.
Sorry.
Okay, so here's the roadmap. Here's the plan. So first, I want to get on the table the logical distinction and the psychological distinction that I want to focus on for these experiments. This is the difference between individual versus group implicating meanings and object file versus ensemble representations. And then I'll quickly go over some prior work showing that sentences with every seem to trigger ensemble representations, at least relative to sentences with each. And then we'll come to these, the brand new experiments here, testing the other half of that prediction so that each triggers object file representations, at least relative to every. So that's the plan. First, let me just talk about this distinction between individuals and groups. And to do that, let's get a couple hypotheses on the table about what the meaning representations might look like. So there's many ways that we, as theorists, might want to describe the meaning of something like every circle is green. One way would be like this: for each individual thing, if it's a circle, it's green. So that's an unrestricted first order specification. So it's unrestricted because the expression itself doesn't restrict the domain in which the quantifier is evaluated. Context might restrict the domain to just the stuff that's on the slide, for instance, but the expression doesn't say anything about the domain. So it just says for each thing that's in the domain, if it's a circle, it's green. Okay, this one's first order because it's completely done in terms of individual things. This kind of first order specification will work for like each and every and some, but it won't work for quantifiers like most. And so people move to a more expressive notation that would generalize to other quantifiers. In particular, the idea here is that every circle is green expresses a relation between two groups of things. So like the circles are included in the green things, or like the circles are a subset of the green things. So that way of writing down the meaning is an unrestricted second order specification. It's unrestricted because the domain is still just the universe, but it's second order because now you're dealing with a whole group of or a set instead of just individuals. Actually, you got two independent groups, circles and green things. One alternative to that, less expressive, would be to get rid of the relational aspect and just describe every circle is green as something like the circles are such that all of them are green. So this is saying, zoom in on the circles, ignore the other stuff, exhaustively predicate greenness. This is still second order because you're still dealing with a group, the circles, but now you're not relating the circles to the green things. You're restricting your domain of quantification and saying within this new domain, everything's green. So there's no mention of a second group. And then we could go one step further and specify the meaning in a way that's still restricted, but it makes no reference to groups. So this would be something like the individual circles are such that each one's green. So still restricted because the expression itself restricts the domain to just things that are circles, but you're saying, well, within this domain, each individual thing is green. And so now, like the one I have at the very top, this is first order in that it just considers individuals and associated properties. So these are four ways you could write down the meaning of every circle is green. And the question is, which one of these is a better description of the meaning representation in a speaker's mind? So like it's represented, it's going to be represented in some format. Which one's the format in which it's represented? And in some past work, including the stuff that we presented last year at CUNY, we tried to argue against the unrestricted idea in favor of the restricted idea. And so today I want to just talk about this other distinction between first versus second order, between individual versus group implicating meanings. And what I want to ultimately argue is that every has a second order group implicating meaning representation, whereas each has a first order or individual implicating representation. And there are a lot of different ways you could formalize this distinction. The way I'm doing it here is just to say that there's different variables in the representation. So the second order one for every has this variable that can take on multiple values at once. So like the big X there can refer to multiple circles. Whereas the first order version, each version has a different kind of variable that can only take on one value at a time. And so second order allows for grouping the circles, first order calls for treating them as individual things. So that's the idea behind the logical distinction. And the idea behind the corresponding psychological distinction is that there's two different cognitive systems. So the individual implicating meaning invites you to create object file representations. And an object file is basically like a pointer to an individual object with some properties that are bound to it. I made a quick demo here of what it feels like to represent object files, though I wonder how well this will work over Zoom, given the problems we've already had. But the idea is you can track these circles around the screen. So there's a bunch of circles moving around and they're going behind this occluder and they're changing color. And the fact that they go behind the occluder or change color, it doesn't make you feel like you're tracking a brand new individual. Those kind of properties are sort of incidental to the tracking of the individual. So that's what it feels like to represent an object file, individuate something in space, bind properties to it like shape, color. And so the idea is, if you're thinking this first order thought, individual based thought, that's an instruction to cognition to engage with this object file system. Okay, so then on the other hand, the proposals that the second order group-based representations invite you to create an ensemble. And an ensemble is essentially just a pointer as well, but it's a pointer to multiple different objects at once. And the way that this is achieved is by abstracting away from the whole group and encoding it in terms of summary statistics. So sorry, abstracting away from the individuals in the group. And so to give you an example of sort of how that feels, we could look at a display like this and say, well, which side has more circles? And so that time it's the right, and that time it's the left. So it's very easy. You create two ensemble representations, you compare their cardinality, and cardinality is one of those summary statistics, but other ones include things like the center of mass, the density, the average size, the level of homogeneity in the group. So these are all group properties that you can use to represent multiple objects at once as an ensemble. So two separate systems, ensembles and object files. They're two different ways to represent the same things in the world. And they're related to these two distinct hypotheses about the meaning representations. The first order individual implicating representation and the second order group implicating representation. And the idea is those kinds of representations serve as calls to these different underlying cognitive systems. So that's the distinction that we're after here. And I'll just want to say really quickly, that's of course not the only difference between each and every, and there's a lot of other really interesting differences that have been discussed in the literature. I mean, for example, scope differences between these quantifiers. And so like this distinction isn't meant to exhaust all there is to say about the quantifiers and what people know about them. It's just the one I want to focus on here. And so now what I want to do is think about, well, what behavioral predictions does that difference make and how can we test them? And I'll start with some data about every triggering ensemble representations, and then we'll get to the brand new data, that's the flip prediction. So here's the idea. We have two different representations, and the general linking hypothesis behind this work is that we can look for whether the different related cognitive systems are active when people are deciding whether the sentences are true or false. And so to take this quote here from Lids et al., people are biased toward verification strategies that directly compute the relations and operations expressed by the semantic representation under evaluation. Okay, so what does that mean? So that means if you have an each thought, by hypothesis, it's a first order thought about individual circles. And now suppose you want to evaluate it for truth. The simplest thing you could do is create object files, which encode each object's individual properties, like color. And that's not the only thing you could do, of course, but that's just the path of least resistance. On the other hand, let's say you have this every thought. By hypothesis, that's a second order thought about a whole group of circles. And you want to evaluate it for truth. You create an ensemble representation of the circles. In doing so, you encode things like summary statistics, like the number of the ensemble, and you abstract away from individual properties. So you don't encode things like the color of particular circles. So here's one way we tried to get at that. First, people see a statement like every big circle is blue or each big circle is blue. They have to evaluate that sentence with respect to a picture of different circles, different size, different colored circles. And you'll notice in these pictures, I have medium circles that have little holes in the middle, which is just to help people tell them apart from the other sizes. But we train them before they do the task, so they know those are actually circles and not donuts. So you have to judge the sentence as true or false. When you're done, you get a follow-up question that asks you about the cardinality of one of the arguments. So how many big circles were there? How many smalls? How many mediums? And here's the thought. If you represented the argument with an ensemble representation, you should remember how many there were. And so number is one of these ensemble summary statistics. So if you represent the circles as an ensemble, you'll remember the number. If you represent them as individuals, you shouldn't encode the number to the same extent. And so the question is just, do you have better knowledge of that number after you evaluated every statement versus an each statement? Even though the answer to both of them is the same. And so to find that out, we fit people's performance on this task to a model of number estimation that basically just says response you give equals number you were shown raised to the power of accuracy. So a perfect score on this kind of question would be getting an accuracy of 1, which would mean on average, if I show you 30 circles, you're responding with 30. But in fact, people underestimate the true number. And so the question is going to be, well, how much do you underestimate the actual number you were shown? And does that differ if you first evaluate in each sentence or in every sentence? And we got Bayesian estimates of the accuracy parameter for each condition. So that's on the x-axis, I'll plot the accuracy parameter. Higher is better performance, lower is more underestimation, worse performance. Y-axis is probability density over the parameter estimate. First, I'll show you distractor trials in the bottom half of the screen. These are cases where if you evaluated every big circle is blue, the follow-up is how many small circles were there. Okay, so this you should be bad at because you shouldn't have been attending to those to answer the initial question, but you should be equally bad in both conditions. And that's what we find. So no matter whether the initial question is each or every big circle is blue, you don't know the number of small circles. So that makes sense. More interestingly is the target trials up top. These are cases where if you evaluate every or each big circle is blue, you then get asked about the bigs. And what we see is that performance following every is better than performance following each. And so this is, we've kept everything the same about the task except for the quantifier, just switch it. And then it makes people less likely to remember how many big circles there were if it's each. So the idea here, again, is, well, every gets people to encode those big circles as a group, as an ensemble. As a consequence, they then remember that cardinality. But with each, you're not representing the ensemble, so you're worse at that cardinality question. Okay, so what we've shown here is that every leads to better performance than each when you probe a group property. But of course, it'd be nice to find the flip case where each leads to better performance than every. And so that's the case I want to talk about now. So testing the other half of this prediction. With each, we said you should encode individual properties. So now if we probe something like the color of a particular circle, you should be good. At the same time, every should not lead to encoding those sorts of individual properties because the ensembles abstract away from the individuals. And so you should be bad when we probe that kind of property. And so to test that, we just showed people 3 circles this time. Each one of them has a slightly different hue. And we told participants this is an experiment about color categories. And so we want them to judge sentences like each circle's green, for example, because we're really interested in words like green and what they consider, what they count as green. And so some of these trials are actually really hard. So we used colors from this color wheel above, which all have a constant luminance. And so it's just the hue that differs. And they're normed. So that the plot below is a naming task where people are shown a hue at random from that wheel and asked to name it. And so in our task, some trials use colors that almost everyone agrees on. And then other times we'll include ones that are, say, right on the cusp between green and yellow, for instance. So it makes it a little bit hard to do that, that true-false question. Once people answer that initial true-false question, then the circles disappear for a few hundred milliseconds, and then they come back, but one of them potentially changes its hue. And participants then just have to say, well, did you notice the change? And so this is a change detection task after an each or an every question. And we predict, well, people who answered the each question should be better at detecting the change. And they were. So here I'm just plotting the raw percent correct on the change detection portion of the question or of the task. And what we see is that if you first got an each sentence, you notice the change more often than if you first got an every sentence. And so these are 2 groups of participants who got the same pictures. They ended up giving the same answers to that initial question about whether each or every circle is green. And actually, there's no difference in reaction time. So they looked at those displays for the same amount of time before they decided. But people who got the each statement initially were just better at detecting a change. So we replicated the effect in another way. Here we got a new group of participants to take part in the staircase version of the experiment. So now if you get the change detection trials correct, it makes it harder on you. If you get the trials wrong, it makes it easier on you. So now people in both of the conditions end up getting around 70% accuracy on the change detection portion. And the dependent measures how easy or hard was the experiment. Up is easier on this plot, down is harder. What that means is that up, easier trials, the colors are drawn from a wider distribution. So the new color might be farther apart from the original. Down means the colors are drawn from a narrower distribution so that they were more likely to be close to the original hue. And what we find is that when you just swap each for every here, this drastically changes people's performance on the change detection task. So the people in the every condition needed easier trials to keep pace with the people in the each condition. And I think this result really surprised me because in these sorts of displays, we only gave 3 objects at a time. That's within your working memory limit. So if you want, you could just encode all 3 colors to make sure you do well on the task. And there's over 80 trials, so you know you're going to be asked a question about whether a color changed. But I think what we're seeing here is the weight of the meaning pushing you in a direction of using a strategy that's not really how you should be approaching the task. So those each statements, they're getting people to represent circles as object files. So they're doing a good job at encoding individual properties and answering this change detection question. The every sentences are encouraging them to treat the circles differently. And so they tend to abstract away from that individual information and don't encode it as often and don't do as well. And so to zoom back out, this offers some evidence that every has a meaning representation that implicates a group, that triggers people to represent ensembles when they go to verify a sentence with every, and that leads them to encode these group properties like the cardinality. On the other hand, each closely related each has a meaning representation that's specified in terms of individuals. It triggers people to represent object files when they go to verify in each sentence, and so they do well when you probe an individual property. Now, the bigger picture moral here is that meaning representations can be pretty detailed and that we can get at them by using supporting cognitive systems as a probe. And given what the special session is this year, I want to mention that this way of thinking about meaning representations, this raises an interesting acquisition question, because what leads learners to pair each and every up with the right concepts? So they don't get any experiments, they just get speech in context. And so what about that speech in context is going to possibly lead them not just to the right truth conditions, like that each and every are universals and they don't mean some or most, but what leads them to represent those truth conditions in exactly the right way? And to that end, in some other work, we're starting to look at how these quantifiers get used in child-directed speech, because there seem to be some striking differences that learners might be able to pick up on. In particular, a lot of the time when parents seem to use each, they seem to be generalizing over very local domains. So you see a lot of things like these examples I pulled out here. You have to ring up each thing. Could you put a flower on each plate? Whereas with every, they often seem to be going way beyond the local domain. They're saying things like, every time I ask you a question, you say you don't know. You turn into a wild man every time we get out. So these seem to be much broader generalizations. They seem to license some kind of prediction about what's going to happen next time you encounter that situation. And there's a lot more to say about, well, how would these different uses link up with the different concepts? But for now, I just want to note that thinking about meaning representations at this level of detail really makes this question about how kids learn each and every even more interesting than it already was. So thanks. I'll stop there. I hope we're still good on time, Florian.
You're perfectly good. Thank you very much. Thanks for a great talk, Tyler. We have about 10 minutes for questions, and a question to be read out loud has come in as the first one on the Q&A. So this is from Jessie Snedeker. She says, the hypothesis is that there's a categorical distinction between two kinds of meanings, first versus second order. The data clearly shows that there is a distinction, but we can't tell with this design whether it is categorical or continuous. Would it be useful to test other quantifiers, for example, all of? In some respects, every often behaves intermediate between each and all of. Am I right in thinking that you should predict that all of will look exactly like every versus even more group-like?
Right. Yeah. So yes, I mean, so we have done all and all of the in some of these tasks, like in the number task we did, and what we saw there was that when I believe when you had the circles also contributed some level of let's say group representation, so that kind of also pushed you in the direction of, oh, you do well on these number trials. I believe if it was just all circles versus every circle, those ones patterned alike. But you're right. We'd predict, like, all else equal, if it is the categorical distinction, yeah, both of those are going to pattern together. And then there's just some other things that might push you in one direction or another, like maybe the partitive does, maybe the plural NP does. But yeah, right. I think it'd be really good to keep doing these kinds of tasks, like especially the color task we haven't done with all yet. So I mean, I think this is important to do.
Great. The next question is from Jack Dempsey. So we're going to allow you to talk, Jack. Just as a reminder, while we unmute you, everybody can submit questions through the Q&A and they can be read aloud if you instruct me to, and otherwise I will assume you will ask it live. Jack, if you unmute yourself, you can ask your question.
Okay, can you hear me okay?
Yep.
Okay.
Yep.
Hi, Tyler, good talk. So I was wondering to what extent you thought that this the mappings of these representations are due to initial encoding of the entities on the screen, or so for example like the three circles. And I wonder if you think you would get the same effect if participants are first presented with these circles, and then maybe like after a distractor are then shown the sentence. Would people be able to update their representations in memory with these every distinctions and mapping?
That's really interesting. I think that would be a great thing to try to see. Is it actually about driving attention in a certain way and making you encode them in a certain way, or is it about, well, you've got all the information there, what are you going to use when you go to evaluate? Yeah, so that's really interesting. I don't know if I have a particular prediction about it. I mean, I'll say that in some other cases where we've been looking at sort of which sets are you representing and which ones do you use in the verification, there is at least one case where we have reason to think, well, the visual system gives you the superset for free. And so you show them like blue and yellow dots, and the visual system usually gives you the total number of dots for free. But we still see cases where people don't use the total, and they'll instead use the smaller subsets to do a comparison. And so, like, at least in those cases, we think, okay, you have all the information, that's about what you're choosing to use. But in this case, yeah, I'm really not sure if it's about what you're encoding or what you're choosing to use. So I think that'd be a great manipulation to try, yeah. Thanks for that.
Yeah, thank you.
The next question is coming from Amit Almore, if I'm saying the name correctly. We will now allow you to talk, and you can ask your question live.
Hello, can you hear me?
Hi. Yep.
Very interesting talk, thank you. I'm just wondering, and this may be very related to the previous question that you just answered, since what you have here is really kind of a visual task with task demands, and then what you're trying to make inference about is the linguistic representation, or how we interpret, how we create mental representations of quantified statements in this case. How can you really tell whether the effects that you're observing are due to how people perform the visual task or to the linguistic representation? So when I have to verify statements like the every statements, a plausible and likely way to perform the task is to look for exceptions. So I can very easily kind of look for whether there exists something that is not every and answer the question. And that kind of doesn't require that I actually scan the display and look at each and every object, which is exactly what I would tend to do if I have to verify each statement. So this leads us to say that the task performance behavior is different, therefore the encoding, the memory encoding, and that has nothing to do with linguistic representation, simply with kind of the depth of processing and so forth, would likely result in the same effect that you're observing, but kind of the difficulty is really attributing it to one or the other. Yeah, thank you.
No, I fully agree. That's yeah, I mean that's the rub there, is like figuring out when is it okay to say, okay, we're going to chalk up this difference in performance to a difference in the representation, because you need to make sure you've controlled for all the other possible things that can get you to use a different strategy in one case versus the other. One thing I like about this case here is that each and every serve is a nice control for each other. So you show that, well, okay, you can use either strategy to get to the right answer. So you can use this, let's say in the color case, you could use the individual strategy, you could use the ensemble strategy, and they'll both get you the right answer to the true false question equally well. And then what we have to explain is just that kind of difference there that's left when how come with one quantifier you go one way and with one you go the other way. And now whether that comes from, as I've been talking about it, the like lexical specification, or whether that comes from some other difference between the quantifiers. Yeah, I mean, that's worth thinking about and testing explicitly. I mean, maybe there's a little prosodic difference when you read the sentences. And so like that would be a thing to control for and explicitly probe. And maybe there's some other associations. And so that's another empirical question, like what other associations would drive this difference? But yeah, so I mean, I fully agree. That's the challenging part.
Can I add one more point to that, Tyler?
Mm-hmm.
So with respect to the specific idea that for every you just look for a disconfirming item, what we find in that task where the number task that Tyler showed is that you see the same performance on true trials and false trials. So even when it's very easy to find a disconfirming object, you still get the group representation. And so that suggests that there's something more about the meaning than the verification strategy that's driving this.
Yeah, thanks, Jeff. I forgot about that particular part of the question. Yeah, right. So so even on the trials where it's right, exactly what Jeff said, you find the same performance on both sorts of trials that way. Yeah, and these things also, by the way, seem to be invariant to other differences. So, you see the same. Oh, hello. Anyway, sorry. Sorry. So yeah, let's just leave it at that for now.
Unfortunately, in the interest of time, I think we're going to have to leave it at that. Thank you again, Tyler, for a great presentation and really interesting work. There's a number of open questions still, but unfortunately, we can't get to them here. We can get to them later. As presenter, by the way, Taylor, you can answer them in the Q&A window if you want to type them there, but we can also continue discussion on the discussion pages of the individual presentations that are linked from the program. We should now transition to our second talk. Thanking Tyler again. There's no applause transition here, so we're just going to move on. And we should now spotlight Mika Slim, who will be presenting our next talk. And Tyler, we should remove the spotlight. Whoever's doing the spotlight.
Sorry,
right
I'm trying to do the spotlight. Just a second here.
And I will continue the introduction. So our next talk will be by Mika Slim, Peter Lars, and Robert Hertziker. Mika is going to be presenting, and I got the spotlight added, John, I think. Oop. There's Mika. Okay, and Mika is going to be presenting here, and the title of the talk is "Are Logical Representations Quantifier Specific? Evidence from Priming for a Non-Quantifier Specific Representation of Scope." Take it away, Mika.
Thank you very much. Can you hear me?
Yes.
Okay, great. So thank you all for coming to this talk. And I will address research on the question of whether logical representations are quantifier specific or not. Before I get to this bigger question, however, I first want to explain what I mean with a logical representation. So I hope my slides are advancing. So consider this sentence: every man bit a dog. This sentence contains two quantifiers, the universal quantifier every and the existential quantifier a. Because quantifiers assign semantic scope, this sentence allows two ways for which these quantifiers can take scope with respect to each other. Firstly, every can take wide scope over a, which I refer to as the universal wide interpretation. And in this interpretation, it seems that that every man bit a potentially different dog. On the other hand, A can take wide scope over every, which I refer to as the existential wide interpretation. And under this interpretation, there is one poor dog that is bitten by all men. And the configuration of scope is assumed to be represented mentally at the level of logical representations, which are independent of syntactic representations, but we know relatively little about the exact nature of the information specified in these mental logical representations. So especially relevant here is the question of whether the lexical properties of different quantifier words are specified in logical representations, because the assignment of scope seems to be partially determined by quantifier-specific biases. Consider these three sentences: each man bit a dog, every man bit a dog, and all men bit a dog. Each has a very strong tendency to take wide scope, and therefore each man with a dog is very likely to be assigned the universal wide interpretation. Every also has a strong tendency to take wide scope, and therefore also has a preference for the universal wide interpretation. Yet this interpretation, this preference is weaker for every than for each. Finally, all men with a dog has quite a strong preference for the existential wide interpretation. So, given that there are these quantifier specific biases in the assignment of scope, we can ask the question, is the representation of scope similar for all quantifiers? Or is there a quantifier specific representation of scope that encapsulate the biases? So this question was previously tested using the structural priming paradigm by Feynman and Snedeker. And the present study, to foreshadow, became a re-examination of their findings. And this is in no way a predefined plan. It sort of happens over the course of the study. And the present study and Feynman and Snedeker study both used sentence picture matching tasks to test effects of logical representation priming. And this task was originally constructed by Raffay and Pickering. So in this task, people read sentences and have to choose one out of two pictures that best matches the sentence. In the critical prime and target sentences, the sentences are in the critical prime and target trials. The sentences are doubly quantified sentences. Here we have an example of a prime trial in the existential wide condition. As you can see, there was a doubly quantified sentence. Every kid climbed the tree, and one matching picture and one non-matching picture. The matching picture, however, only matches one possible interpretation of the sentence. In this case, the existential wide interpretation. Here is an example of a universal wide prime. And here the only matching picture is the universal wide interpretation of the sentence. This way, participants are forced to assign either the existential wide or the universal wide interpretation to the sentence. Directly following a prime, you present people a target trial. The target trials contain a similar quantified sentence. Here, every hiker climbed the hill. But now the two pictures display both possible readings of the sentence. And if there is priming, which can be defined as the tendency to persist in your interpretation, you would expect that the existential wide interpretation is assigned more often to the target following an existential wide than following a universal wide, and vice versa for the universal wide interpretation. So why is this effect of logical representation priming so interesting? Well, a simplified explanation of priming is that it's somehow easier to reconstruct a representation if it was used in the processing of a previous sentence. And therefore, priming indicates that partial representations are shared between prime and target. And this is what's been found in Raffay and Pickering's study and in some studies following that. Using this logic, Feynman and Snedeker tested whether priming persisted between quantifiers. If priming does not emerge between quantifiers, but only within quantifiers, then it seems that logical representations are differentiated according to quantifier-specific lexical content. But if priming does emerge both between and within quantifiers, it seems that these logical representations do not specify the quantifier-specific properties that account for these biases in scope. So Feynman and Snedeker used this task that I've just showed you with active transitive sentences with the existential quantifier A in the object position, but they vary the quantifier in the subject position between each, every, all, and numeral quantifiers such as 3 or 5. In the case of a numeral quantifier, the number always reflected the total set of agents depicted in the pictures. This varied both in prime and target trials, yielding a total of 16 possible prime-target configurations. And the results showed priming, but only within the quantifier. So there was priming from, say, each kid climbed the tree onto each hiker climbed the hill, but not from every hiker climbed the tree, every kid climbed the tree onto all hikers climbed the hill, for instance. This suggests that logical representations are sensitive to quantify specific biases, and thus that logical representations specify the assignment of scope in a quantifier specific way. This brings us to the present study. So the present study started out as a further investigation of this finding of these findings from Feynman and Snedeker, but now in a Dutch context. Why is this relevant? Well, quantifier words are prone to cross-linguistic variation, and we can see this by comparing Dutch and English universal quantifier words. Dutch universal quantifier words, there are, like English, there are 3 of them, elke, iedere, and alle. Elke and iedere are distributive quantifiers comparable to the English quantifiers each and every. But as we also just saw in the previous talk, there are quite some known differences between each and every. whereas there doesn't seem to be that much of a difference between elke and ieder. Alle, on the other hand, is a non-distributive quantifier that's comparable to English all. So given this, these similarities between elke and ieder, we wanted to know whether we would find priming between elke and ieder. Because possibly the logical, sort of the lexical representations of elke and ieder overlap, resulting to in priming between elke and ieder as well, especially because priming is not assumed to be due to phonological repetition. So we used simple picture matching tasks in a Dutch context, similar to the trials that I've just shown. We conducted it over the internet and analyzed the results using locate mixed effects models. The prime and target sentences were doubly quantified sentences with a universal quantifier in subject and the existential quantifier un, which can be translated as a, in the object position. In the prime sentences, we varied the subject quantifier between elke, ieder, or alle, whereas in the target sentence, the quantifier was always elke. So this gives us 3 possible prime quantifier configurations. We tested priming from elke onto elke, which is a within quantifier condition, and following Weber-Snedeker's results, we would expect priming here. We tested priming from ieder onto elke, which is a between quantifier condition, but we assume quite some meaning repetition here, so we may find priming here as well. Finally, we tested priming from alle onto elke, which is a between quantifier condition, and alle and elke have quite clear different scope-taking tendencies, so here we did not expect to find priming. In our first experiment, we manipulated prime conditions, so where the prime trials were given in the universal wide or in the existential wide condition within subjects. Prime quantifier, on the other hand, was manipulated between subjects. And this design is similar to Weber-Snedeker's experiments. So here are the results of experiment 1. The y-axis here shows the mean percentage of universal wide responses in the target trials, and the x-axis shows the different prime condition and prime quantifier conditions. The black horizontal bars represent the mean rate of universal wide responses in all these conditions. As we can see, that this black bar is always higher in the universal wide prime condition than in the existential wide prime condition. In other words, there seems to be priming. In the elke condition, this was a significant effect. In the ieder condition, this was not a significant effect. And then finally, in the alle condition, even though this was descriptively the smallest effect of priming, we found a significant difference. Taking these results together, we find an effect of prime condition, an interaction between prime condition and prime quantifier, and pairwise comparisons on the full model showed that there is weaker priming in the ieder to elke condition compared to the other two. So descriptively, we find stronger priming in the elke to elke condition. We do not find priming in the ieder to elke condition, but maybe there's a bigger difference between ieder and elke than we expected. And the biggest puzzle is that statistically, we also find priming in the alle to elke condition, even though this was descriptively a very small effect. So these results were somewhat inconclusive. And one thing that we wanted to test and hopefully rule out is whether the priming in alle to elke was a false positive. So therefore, we replicated experiment 1 in experiment 2. In experiment 2, however, we manipulated not only prime condition, but also prime quantifier within subjects. This way, all participants saw the same conditions throughout the experiments, and we hope to reduce a possible role of individual variation this way, because maybe, and this was not necessarily a very clear hypothesis, but one thing that we thought of, that maybe in the alle to elke condition of experiment 1, there were just quite some people that showed a small yet consistent effect of priming, and this way we wanted to rule out whether that was due to individual variation or whether it was due to a true effect. So the only change in experiment 2 compared to experiment 1 was this prime quantifier manipulation within subjects, yet the results show a complete different story. In this design, we have an effective prime condition and no interaction between prime condition and prime quantifier. So there is reliable priming from elke onto elke, from ieder onto elke, and from alle onto elke. So with this design, we find comparable priming in all 3 prime quantifier conditions. And this means that experiment 2 does not provide evidence for a quantifier specific representation of scope, because priming within the same quantifier was comparable to priming between quantifiers. The question is, of course, why this difference in design between experiment 1 and experiment 2 causes this difference in results. One thing that we could think of is that in within subject design, all participants are exposed to a within quantifier condition. And of course, priming is known to be merged in this within quantifier condition. So maybe this priming flows over to the other conditions as a result. In other words, this somewhat simplified hypothesis assumes that priming between quantifiers is driven by the presence of a within quantifier condition. In order to test whether this is the case, we conducted an extra experiment in which we manipulated the presence of a within quantifier condition between blocks. One block, which I will call the inclusive alkyl block, contained the within quantifier condition as well as the between quantifier conditions. And here we would expect priming between quantifiers because there is a within quantifier condition present. Second, we had the exclusive alkyl block that only contained both possible between quantifier conditions, so priming from either onto alkyl and priming from alle onto alkyl. And because there is no within quantifier condition present in this block, we wouldn't expect priming between quantifiers if it's indeed the case that priming between quantifiers is driven by the presence of a within quantifier block, unless maybe if it's the second block in the experiment. And block order, so whether the inclusive alkyl or the exclusive alkyl block was presented first or second was also manipulated. So this brings us to results of experiment 3. Note that this graph is somewhat different than the graphs I showed in experiment 1 and 2. Here we can see the mean percentage of universal wide responses broken down in the block and block order conditions. It doesn't show the prime quantifier conditions, just simply for the interest of time. Importantly, we can see that the graph shows that the universal wide response was selected more often in universal wide prime condition than in the existential wide prime condition. So the black bars are higher in the grayish blocks than in the white blocks. And this effect of prime condition wasn't only significant, it also did not interact with any of the other possible manipulations in this experiment. So there was no effect of block order, or prime quantifier on prime condition. Rather, priming just occurred all across the board. This suggests that priming between quantifiers is not dependent on the presence of a within quantifier condition after all. Rather, it seems that priming between quantifiers emerges if multiple prime quantifiers are shown to the participants, and also if those are multiple between quantifier conditions, as was the case in the exclusive alkyl block of this last experiment. So, summing up, we conducted 3 experiments to test whether logical representation priming emerged within and between quantifiers in a Dutch sentence-picture matching task. In experiment 1, we found that priming was descriptively stronger within the same quantifier than between quantifiers. Statistically, these results were not as clear. And here we manipulated prime quantifier between subjects. In experiment 2, we find comparable priming between and within quantifiers. And here prime quantifier was manipulated within subjects. So this change in design caused for a difference in results. Finally, in experiment 3, we also find comparable priming between and within quantifiers, again in a within subject design, and also regardless of whether the participant is exposed to a within or to a within quantifier condition. So it seems that in a within subject design, participants somehow seem to generalize the scope assignment and the representation of scope across different quantifiers. And the within quantifier boost, so the effect that priming within the same quantifier is stronger than priming between quantifiers, is highly dependent on the experimental design. It seems to emerge only in a between subjects design, but not in a within subject design. And this was corroborated by a meta-analysis of the results, which also included famous Snellekes data that we conducted by means of cross-experimental analyses. So this brings us to the discussion. So our results seem to suggest that under the right experimental design, people can generalize in the scope-taking behavior of different quantifiers. And we think that this is due to effects of adaptive learning, which is the effect that people can adjust their biases and expectations about language use and incoming linguistic input based on the linguistic input provided in the local environment. Recall that the doubly quantified sentences are actually associated with quite strong preferred readings, and therefore people are not only biased about a certain for a certain reading for a certain type of doubly quantified sentence, but they also expect to encounter this reading more. So for instance, the target sentences with Elke are expected to require the universal wide reading more often than the existential wide reading, similar to sentences with each and every. In our experiments, however, the participants were presented equally often to the existential wide and the universal wide interpretation of the prime trials, because half of the primes were given in the existential wide interpretation and half of the primes were given in the universal wide interpretation. So based on this input given in the experiment, people may adjust and adapt their preferences in interpreting the doubly quantified sentences. In a within subject design, like in experiment 2 and 3, participants are, of course, exposed to the universal and the existential wide interpretation equally often of multiple types of doubly quantified sentences. And with multiple types, I mean multiple quantifiers in the sentences. And therefore, they are expected to adjust the bias on the scope taking properties of the multiple quantifiers, but also they may learn that all these different types of sentences are actually ambiguous between the same two interpretations, namely between an existential wide and universal wide interpretation. This may lead to a generalization in the scope assignment of these multiple quantifiers, and thus the priming between quantifiers. However, we must say that this can explain the patterns of the results in our study, but it does require further investigation. I want to come back and finish this talk by looking at the big question that I asked in the beginning, and that's whether logical representations specify the scope-taking biases of quantifier words. Our results do not suggest that there is a quantifier-specific representation of scope in these logical representations. Priming between quantifiers does seem to be more constrained than priming within quantifiers, but if there is priming between quantifiers, the size of priming is comparable to within quantifiers, and this suggests that these representations are similar in the end across all these different quantifier words. Rather, of course, it seems that quantifier words do guide the interpretation of scopically ambiguous sentences. Of course, there are these biases, but these lexical biases seem to be represented at another level than the logical representations primed in this study. And it must be said that quantifier words are not the only source of information that are used in interpreting a scopically ambiguous sentences. So also the order of the quantifiers in the syntax or in the sentence or context or prosody can all guide scope ambiguity resolution. And the current study does not elucidate on how these different cues can guide and interact in scope ambiguity resolution and thus in the construction of a logical representation. I want to end this talk with a small warning message, so to speak, and that is, of course, that we only tested the representation of doubly quantified sentences with a universal quantifier and an existential quantifier, and therefore we must be careful in overgeneralizing the results to all other types of possible quantifiers. So on that note, I want to thank you all for attendance, and I'd be happy to address questions and comments.
Thank you very much, Mika, for a wonderful talk. As we're getting ready for Q&A, a reminder for those of you that may have just joined, you can submit questions through the Q&A feature. You can, if you just put it there, I will call on people and will ask you to unmute yourself. If you specify you'd like it to be read out loud, I will just read out the question. And before I turn to the first question, another pointer, I'm going to share the links to the discussions. This one is for the first talk. I forgot to do that after the first talk. On the website for any questions that we do not get to during the Q&A. So I'll post the one for Mika's talk at the end of our Q&A. So first we can focus here. First question to be read by Jesse Snedeker. One limitation of this method is that there's always the possibility of picture priming, learning to select pictures with the same conceptual, perceptual properties independent of sentence meaning. Picture priming could easily be adaptive too. For this reason, I find the results most compelling when we have closely matched cases that do and do not show the effect. I wonder if some of your manipulations may have nudged folks to focus on the pictures, varying quantifiers within subjects. How are you ruling out the picture priming?
Yes, that is a good question. So visual priming is indeed, or could be, an influence in this task. So let me get back to the slide that shows the task. These materials were taken from one of my previous studies. And well, in that experiment, in that study, we actually ran a control experiment to test for effects of visual priming. And in that experiment, the sentences were replaced by small figures that in the prime sentence, in the prime trials, were only present in one of the pictures, whereas in the target trials, they were present in both of these pictures. So for these prime trials, the picture would be the tree or the ladder. And in the prime trials, it would be, and in the target trials, it would be the hiker. So by using this non-linguistic not sentence picture matching task, but picture matching task, we actually found that there wasn't an effect of visual priming, even if they are only forced to focus on the visual information of the pictures. And because we use exactly the same materials, we ruled out visual priming in that way. So yeah, but of course it could be it could be an influence, but I don't really think there's reason to believe that it is the explanation given this control experiment.
Great, thank you. I have a question as well myself here. So I'm curious about your thoughts with regards to what gets primed. So this is, Jesse's question got at one angle of this, but from the sort of linguistic form and potential underlying logical form type of representations, one could imagine with your type of setup that indeed it's the sort of general conceptual nature of the, say, existential wide scope that sort of representation gets primed. An alternative could be that whatever process theoretically you posit as underlying the deriving of, say, an inverse scope reading in particular, right? Whether that's through quantifier raising or through some other mechanism. And it would be interesting to know which one of the two is at play in your data here. And I wonder if you have any thoughts, whether your data speak to it, or if you have thoughts on how one might be able to push further on that front.
Yeah, that's a great question. It's sort of becoming the big question in my PhD, actually. Regarding, if I understand the question correctly, you are wondering whether we are priming sort of a logical form representation or whether we are priming the operations involved in constructing such a logical form representation. Do I get that correctly?
Yeah, or for the first option, even some more broader, higher level conceptual representation rather than specific LFs, right?
Exactly.
Yeah.
So
maybe it's three options. I don't know.
I see your point. So let me first go back to what you just said. So whether it's maybe a conceptual representation. So that is actually a sort of an hypothesis that I'm growing very sympathetic towards, because I think that at first the findings for Feynman and Snedeker are actually quite difficult to reconcile with the idea that's just this conceptual, possibly mental model of the sentence, of the interpretation of the sentence, just because there are clearly these quantified specific differences. Our results show that maybe it is actually a sort of a conceptual interpretation after all, sort of conceptual representation of the sentence meaning. So it's definitely something that could be happening, and I actually just think that it requires further testing, because at the same time we can't really rule out whether it's like a pure logical form as of now, I think. Regarding whether it's the operation or the representation, so to speak, that you tested, there is actually a study of Schemmer and Bott that actually tried to manipulate priming of representations and priming of operations. So in some of their trials, the operations, so the inverse scope reading, was shared between prime and trial, whereas the representation was not. And they didn't find results there. So it seems that it's actually at the level of the representation after all. But yeah, that's nothing I did myself. If that answers your question.
Yeah, absolutely. Thank you very much. Again, reminder, you can submit questions in the Q&A. If you're here as a panelist, you can just put it in the chat, private chat to me, and I will see it then. So if we have other questions coming in. Here's a question by Roman Feynman to be read. A similar concern to Jesse's is priming of verification strategy. On that story, it's not picture similarity alone that primes, but the application of a similar strategy for checking the picture against the sentence. So the locus of priming is still not LF, but it does require similar sentences. We found evidence of this kind of priming in this kind of task in Feynman, Maldonado, and Snedeker 2020. That's the end of the question.
Oh, okay, yeah. So, so I actually I've read that study, and actually based on that study, I think that it's maybe not necessarily the case what's happening here, because if I remember correctly, they actually did a reevaluation of the Shyama bot study I actually just mentioned, and they found that priming could also occur from whether the prime trial required a verification from looking from left to right or looking from up and down. Or something like that, because the pictures were not really these naturalistic scenes, but rather just figures displayed in a certain way. And here we actually do use these naturalistic scenes. And I don't really think that there is always a way to, because I think that pictures that you see on the screen here are quite representative for all pictures. And it doesn't really seem to be the case, or I can't really think of a way that you would verify these pictures solely by looking maybe from up and down or from left to right. I think in order to verify what is true, you have to really see the full picture, because it's always an agent interacting with an object in some way. But maybe, yeah, I think if that was the question that was asked, I hope that this is an answer.
Thank you. One other small comment or suggestion for further things to look at, although admittedly things may get quite hairy in that regard, but right, so in the semantics literature, there's of course lots of discussion of possibly different ways of achieving wide scope, especially for indefinites, with choice function analyses and so on being on the table, where say something like quantifier raising is not available from embedding in certain syntactic islands and so on, right? So if one were to push further on the operation type of question, it could be really interesting to compare whether, say, you know, something that could at least be derived by QR has any priming impact on something that could only get a wide scope indefinite reading with, you know, some other choice function or scope taking mechanism. I don't know if you have any thoughts or.
Well, I think I think sort of related to this suggestion is I actually think that it could be really interesting to further test these findings with different quantifiers, and indeed also different types of sentences, to get more insight into that matter, but also into what I've just presented before. But I think that if you really want to look at operation, I'm also thinking that it could be a cool idea to not necessarily use priming, but use more online methods, so to speak, where you actually tap into real-time language processing. Because even though I think the priming paradigm is great, it's a problem that it's always somewhat ambiguous, it seems. So one of the big issues, of course, that we've already laid out is that the representation that's being primed is very difficult to isolate. And therefore, I think it could be cool to, or even combine priming with another more online method, for instance, to really tap into real-time language processing.
Great, thank you. So with that, we're going to have to wrap up our question period. I now posted the link in the chat to the discussion page on the CUNY website, so feel free to post any follow-up comments or additional answers there. So please use that. We are now ready to move on to our last talk of this first session. Our presenter is going to be Paul Marti. You can go ahead and share your screen, and we should make sure to spotlight Paul.
Unmute myself.
And there he is. Yes, there you are. This is joint work with Jacopo Romoli, Yasu Sudo, Richard Braheny, and Joe Cohen. And Paul is going to be presenting on What Primes What, an experimental framework to explore alternatives for scalar implicatures.
Yes, thanks, Florian. So yeah, in this talk, we will be concerned with a form of meaning enrichment known as scalar inferences, whereby the literal meaning of an expression is enriched by incorporating the negation of some alternative expression. An example is given in one.
Paul, you're sorry to interrupt. The screen is black right now for Schengen.
Okay, so
now we can see it. It may have been the full screen switch or something of that sort.
So I go again with slideshow. How is it now?
Unfortunately, that goes to black. You may have to go through with the slides like that. We can see them okay like this. It's not perfect, but you can just scroll through them like that.
Wait a minute.
Sorry about that.
So
that shows fine. If you want to just click through like this, that would be perfect.
it's not gonna work for me, right? Wait a minute. Okay. Let me share again. Now you can see it, right?
We can see it right now, yes.
So if I now just share with you, hopefully, what about now?
Yeah, as soon as you do that switch, it goes black, unfortunately.
Okay, so
if you can just scroll through like this in the interest of time, I think that'll be the best. Sorry.
Happening. So I was telling you that, yes, so we'll be concerned with scalar inferences, right? Can you hear me? Yeah, good. Okay, so the example is illustrating the not all enrichment associated with the quantifier sum. And this enrichment process is commonly assumed to involve at least two mechanisms, one for generating alternatives and one for negating these alternatives. And these mechanisms have been investigated in recent years using the structural priming paradigm. And it was found that these mechanisms are sensitive to meaning-based representation recently activated. In a seminal study, Bott and Shemla found that an expression is more likely to be enriched if its enriched meaning has just been activated, and this in comparison to cases where its non-enriched meaning has just been activated. And in a follow-up study, Rees and Bott found that an expression is also more likely to be enriched if a stronger alternative to that expression has just been activated, once again, compared to cases where its non-enriched meaning has just been activated. So these very exciting findings clearly establish that scalar implicatures can be prime, but they leave us with an open question, which is, what is the direction of these priming effects? And more generally, what is their logic? And this is the question we aimed to address in this project. And to do so, we changed the points of comparison and we looked at what people do when their interpretation is not experimentally biased by priming. Concretely, we tested whether implicature or alternative primes increase enrichment in comparison to meaning expectations prior to any form of priming. And using these baselines, we've been able to determine how different primes affect SI computation. And today I will emphasize two aspects of this project. First, I will tell you what we've learned from the comparisons with our novel baselines with respect to the direction of the priming effects. And then I will explain how we used our findings to test different types of alternatives, which have been hypothesized to enter SI derivation, but the status of which is still very much debated in the current literature. This is not the whole project, as we also tested an alternative explanation for the priming effects based on visual similarity. The results are in the abstract. I will not develop them in the talk, but I'm happy to tell you more about this topic in the Q&A. So the upshot of the contribution is going to be that we found that the SI-related priming effects are inverse preference effects, much like those observed in the syntactic priming literature. And this characterization, we will see that this characterization provides a better understanding of how and when SI computation is affected by priming, and we will propose an informal QUD-based account of the priming-induced effects that we found. And now we are ready to jump to the first part, the experiment one. So we designed that experiment to be as similar as possible to the previous priming studies on the topic. And we tested the same three types of sentences as in the previous studies, so sum, number, and ad hoc. So a sum sentence like 2 can be enriched to mean some but not all of the symbols are squares. A number sentence like 3 can be enriched to convey that there are exactly 4 squares. And an ad hoc sentence like 4 can be enriched to convey that there is a square and nothing else, or there is just a square if you prefer. Now in the target trials, people had to choose between a weak symbol card and the option to select better picture, which you can think of as a type of covered card. And the weak symbol card depicted a situation that makes the literal meaning of the sentence true, but its enriched meaning false. And subjects were asked to select the visible picture if they consider it a match for the sentence, otherwise to go with the better picture. And the choice here depends, of course, on which interpretation is derived for the sentence. The idea is that we can use the proportion of better picture selection as a proxy measure for enrichment. Now in the prime trials, here, subject had to choose between 2 symbol cards, and they were asked to select the card they considered a best match for the sentence. We had weak primes and strong primes. Weak primes on the left involved a weak and a false symbol card. And for these primes, participants were expected to select the weak card solely based on the literal meaning of the sentence. Strong primes on the right involved a weak and a strong card. And here we expected people to select the strong card, that is to favor the enriched meaning, because only that meaning provides a non-arbitrary way to resolve the task. And prime conditions consisted of a target trial immediately preceded by either 2 weak or 2 strong primes. Now, following the design in Bott and Schemler, our filler trials involved canonical alternatives to the 3 expressions tested and 2 cards in the configuration similar to the primes or to the targets, as you can see with these examples. Now the real novelty in the study comes from our proposal for establishing neutral baselines. So such baselines are completely absent from Bott and Schemler's and recent Bott studies. There is yet a previous proposal in Walden and Deegan where the baselines are mixed with the test priming conditions. However, in our study, what we needed our baselines to inform us about subjects' meaning expectations prior to being exposed to any form of priming. And in particular, we really wanted to avoid that subjects' responses to the baselines be affected by what people see or what they do in the test priming conditions. And so for that reason, we adopted a blocking design. And so our baselines, that's very important, our baselines were individual unprimed target trials, and they were all presented in a separate block prior to the prime target trials. So we ended up with 2 blocks. First one included all unprimed target trials, which you see on the top row, which we already described. And we also had control true and control false trials in this block. For these control trials, there was a correct and an incorrect choice, but the correct choices did not depend on which interpretation participants derived. The second block included all prime target trials. There were 2 types of weak and strong, which we already described. We recruited 56 native speakers of English online through Prolific, and each of them completed the 2 blocks of trials in turn. Now, regarding data treatment, we had the pre-established threshold of 80% accuracy on control trials. And as in previous studies, we just removed all responses to prime target trials not preceded by the 2 correct prime responses. We analyzed responses to the unprimed and prime target trials by modeling a response type likelihood using logit mixed effect models. And now we are ready to see the results of that first experiment. So this graph here depicts the proportion of better picture selection to target trials, which is our proxy measure for enrichment for each expression type, so ad hoc, sum, and number. by experimental condition. So strong in red and weak in blue. Baseline is not displayed yet, but it will be in gray. And the first finding we see here is simply that we replicated the within category priming effects from the literature. So for each expression, participants selected more often the better picture option after strong primes than after weak primes. So, but now the novel and most interesting part comes from the comparison with the baselines. For number, first of all, the baseline rate was above the strong rate. And this is telling us that the priming effect here is driven by the weak primes. It suggests further that exposure to the weak primes also affected participants' responses to the strong trials in decreasing slightly the frequency of enrichment. Now for ad hoc, on the other hand, the baseline rate was below the strong rate, evidencing that the priming effect here is driven by the strong trials. The baseline was in the high mid-range, a bit below but not significantly below the strong rate, evidencing that the priming effect is probably primarily, but not completely, driven by the weak prime. So now, what's the take-home message here? So we tested 3 expressions, and we ended up with 3 distinct profiles. So what's the logic of these effects? Well, the logic is that all these effects are inverse preference effects. And so for each expression, the more effective prime is the one priming the interpretation less expected by speakers in the study, as established by our baseline. So for number, the enriched reading appears to be the most expected one. And in that case, the weak primes are more effective at changing these expectations. For ad hoc, it goes the other way around. And some is a sort of in-between case, as we saw, neither meaning really dominates. And both kinds of prime can affect the priors in a way that we detected in our outcomes, and we will see more evidence for that in experiment 3. Now, based on these findings, we propose that one way to model the priming effects here is to think of them as adjustments of prior expectations on questions on the discussion, or QUDs for short. The idea is that in the critical target trials, people may assume different QUDs, which is going to influence in turn what alternatives are relevant and whether meaning enrichment is called for. For a number sentence, for instance, like the one we see here, there are 4 squares, people can assume a how many question, which favors the enriched reading, but they may also assume a yes/no type of question, which is going to favor the literal reading. And as we saw for number sentences, there is a strong prior preference for how many QUDs, which is therefore the most expected one. If we follow that line of reasoning, then we can think of the strong and weak primes as queuing a particular QUD. So strong primes tend to queue how many questions, while weak primes tend to queue a yes/no question. And what inverse preference effects show is that exposure to the prime type prompting the less expected QUD leads speakers to adjustments of their prior expectations. In the case of number, it's the weak primes. Now back to the broader picture, our results so far, results from experiment 1, show that only the priming effects for ad hoc are due to clearly above baseline rates. And now, since recent bot studies showed that they found no difference between strong and alternative primes, we can actually expect that alternative priming to facilitate SI computation for ad hoc as well. So we put that expectation to the test, and we took the opportunity to test different theories of alternative. So we are moving to alternative priming here, experiment 3. And in that experiment, we added the alternative primes from recent bots with an interesting twist for ad hoc. So for ad hoc, we tested first the canonical conjunctive alternatives. So for a sentence like there is a square, these alternatives are there is a square and a circle, there is a square and a star, etc. And together with the base sentence, the negation of these stronger alternatives gives us that there is a star and nothing else. But in addition, we tested non-recurrent alternatives. which are of the form, there is a circle, there is a star, etc. And those alternatives are logically independent. But crucially, such alternatives are hypothesized on some theories to enter a side derivation. And indeed, it is easy to see that the negation of these alternatives together with the base sentence is giving us the exact same output as before. There is a square and nothing else. So our reasoning here was that if alternative priming boosts ad hoc implicature, then we can use alternative priming as a way to test what type of alternative enters the psi reasoning for this type of implicatures. So we got three types of primes, weak and strong as before, and the novel alternative primes. For ad hoc, there were two types of alternative primes, stronger and non-weaker. And for the other two expressions, all alternative primes involved canonical stronger alternatives to the relevant expressions. So all for some and 6 for 4. We use the same blocking design as in the rest of our experiments with two refinements. First, we grouped the primes in 3 groups of the form weak plus test, where test could be strong, stronger alternatives, or non-weaker alternatives. And each participant only ever saw one type of test prime. And we designed the experiment that way to minimize cross-priming effects, which could hide certain differences in strengths between test primes. The second major change is that we replaced the sentences in the figures. So in that experiment, alternative sentences were only used in the alternative primes. We recruited novel participants online. They were pseudo-randomly assigned one type of test primes and random survey. The rest of the procedure was the same as in experiment 1. Data treatment was also the same as in experiment 1. And in the analysis, this time we built our models to look at the effect of condition, group, and the interaction, so as to detect potential differences between different types of test primes. And we will start here with the results for sum and number. So what you see on this graph is the proportion of better picture selections target trials by prime condition and prime group, so the strong group on the left and alternative group on the right, not yet displayed. The result for the strong group replicated to a large extent those from experiment 1, with some minor difference for some, which I'm happy to go back to in the Q&A. Now, the comparison between the strong and alternative groups showed that the baseline rates were similar in both groups, but that the rates for test and weak were systematically lower in the alternative group. In other words, subjects generally did less enrichment in the priming conditions for the alternative group than in the priming conditions for the strong group. In sum, we found no evidence that alternative priming facilitates enrichment for sum or number. However, we did find evidence that alternative primes are less effective than strong primes at countering the effect of the weak primes. And we describe here that these findings are consistent with Heisenberg's conclusion that activating alternatives automatically lead to SI derivation. Now we believe that this contrast between strong and alternative primes can receive a QED-based explanation as well. So once again, let us assume that speakers are trying to figure out an implicit QED in the target trials. And they may end up with a strong exhaustive QED or a weak non-exhaustive one, like a yes or question. Now, if we compare the strong and alternative primes, we can see that the strong primes are actually better cues for strong exhaustive QEDs. And the reason for that is that alternative primes can actually cue either type of QEDs and therefore deliver us with more uncertainty. And that difference could explain the contrast that we found. Now turning to the last set of results, the results for ad hoc. The results for the strong group replicated to a large extent those from experiment 1, with some minor difference here regarding the baseline, which I'm also happy to go back to in the Q&A. Now for the stronger alternative group, we found a priming effect with tests above baseline, as in the strong group. However, subjects did less enrichment in this group than in the strong group. It is also true of the last group, but for non-weaker alternatives, we didn't find any priming effect to begin with, and no difference at all with the baselines. So to summarize, we found evidence that alternative priming facilitates ad hoc implicatures, but only with stronger alternatives. Yet alternative primes are not as effective as strong primes. And finally, we found a contrast between stronger and non-weaker alternatives. And this contrast is expected, for instance, if we assume that only stronger alternatives can enter a side derivation. Otherwise, this contrast needs to be explained. So we can ask, well, what could be the explanation? There is a possible explanation, but more like a speculation in our QUD framework, which would be to say, I mean, the idea would be to say that conjunctive statements are perhaps more likely to be understood as addressing mention all QUDs, in which case there would be better primes for enrichment when it comes to the target. We also note that conjunctive yes/no questions are actually good triggers for ad hoc implicatures in such cases. So suppose that alternatives of the form X and Y, a QUD of the form is there an X and a Y, then an answer like there is an A is going to be naturally enriched in order to count as an appropriate answer. So that could also explain the discrepancy. That could explain, sorry, the discrepancy that we found. Now, time to wrap up, to conclude. So what did we learn about implicature priming? Well, the direction of the effects is largely predictable from the base rates of enriched interpretations. And for that reason, they can be, I mean, what we've seen is that they can be modeled as inverse preference effects. We've also seen that the more effective prime type for a given expression can have wide range effects. And these cross-priming effects obviously need to be considered when designing such experiments to make informed choices about how we block trials, how we group primes, what materials we use in the fields. Next, what did we learn about alternative priming? Well, these effects can also be modeled as inverse preference effects. However, crucially, alternative priming is less effective than implicature priming. And there is probably a simple explanation for that, which is that there is just no equivalence between activating the mechanisms for SIs and activating an alternative. There is, in fact, as it seems, a natural asymmetry here between the two. Finally, we tested different types of alternatives for ad hoc. We found above baseline alternative priming effect, but only with stronger conjunctive alternatives. As we said, this finding is directly accounted for if only stronger alternatives enter a side computation. Yet we've been more cautious, and as we explained, this discrepancy could potentially receive an independent explanation, and we offered one in our informal QUD framework. Thank you.
Thank you very much, Paul. I'll applaud for everyone as usual. So we have about 7 minutes left for discussion and questions. Again, for everyone, Q&A works through the Q&A icon in your Zoom tray. Just click on that and submit your question, and I will call upon you. I can also read questions aloud. Questions from the panelists should be sent to me by private chat since they can't post questions. I have a question to start with. Going back all the way to experiment 1. In some way, it may be a little more on the detailed side, but I was curious how it fits into the larger picture. So this is about the difference between how the baseline interacts with the strong condition for the sum and the numeral cases, where for the numeral you find that strong priming gives you lower rates than the baseline. And I just was curious what more you had to, maybe I missed something, but I was curious what more you had to say about that case and how that related to the sum case.
Yeah, and it's a good reading of the graph. And it's in fact, so this observation, this finding that quite systematically the rate of enrichment for the strong primes is lower than the baseline. the baseline rate for numbers is something that we found in all the experiments that we conducted. Naively, if you look at that, you might just think, well, you had 2 blocks of trials. So the gray bar is block number 1, and the red and blue bars are block number 2. So maybe just people got tired at some point and they stopped doing enrichment for numbers. But we know that based on the findings for the other expressions, that's not what they did. So no. So the more reasonable explanation for that is that in the case of number, the most effective prime type is the weak type. And I think what this shows is that we have cross-priming effects here. So people start seeing the weak primes, they start changing their expectations. And this has a direct impact also on what they do in the strong trials. And in fact, if I can just draw your attention on the fact that even though we didn't find this in the first experiment, we found in experiment 3 a very similar effect for ad hoc. Right? It's in fact the mirror effect. So if you look at that, this is the results in the strong group, right? And what we found in experiment 3 is that the enrichment rate for the weak prime condition is actually now above the baseline rate. And if you can think of it as just a mirror effect, because in the case of ad hoc, the more effective prime type is the strong primes. And as you can see, it seems to also have an effect on what people do in the weak trials.
Interesting, thank you. There's questions coming in. The first one is to be read out loud by Nadine Bade. She says, it seems like your results speak against a structural view on alternatives for ad hoc scales. It seems to me that approach would not allow the more complex alternative with AND to play a role.
So there is indeed the question of what the different theories on scalar on alternatives allow in the case of ad hoc. So maybe I can go back to the slide where I do present the different 2 types of alternatives. So quite clearly, let's say a neo-Gricean account would certainly only allow the stronger type. So the one there is a square and a star, the conjunctive statement. Now, if you have a structural theory, indeed, the most straightforward way to go is just to replace an NP with another NP, because it's going to be equal complexity. However, if we read carefully the structural theory of alternatives, we will see that the lexicon is a possible substitution source, but the context is also a possible substitution source. So the fact that a conjunction has been presented just before the target is potentially, the effect of that is probably to include in the context just a conjunctive statement that is available to construe the alternative, even though it's going to be more complex than what you could have done otherwise. So I don't think it is a direct, it is not directly against the structural theory of alternatives.
For that time, oh, sorry.
No, sorry.
We have time for one more question. Judith Degen has submitted one that she also asked me to read out loud. Saying Walden and Degen's story for their very similar results is a lexical uncertainty rather than a QED story. Can you say more about why you think a QED story is preferable and what kind of data might help tease apart the 2 accounts?
Yeah, I think indeed that the story here is very, very much in line with what Walden and Degen proposed in their paper. In fact, I just see this as just another way of formulating a very similar idea. Now, what could be helpful for for that kind of story to be backed up would be, for instance, to do a study where essentially we present people with the sort of what we've been using in the alternative primes or in the strong primes, and to ask them what kind of what kind of questions they can think about, what they can think of, what is being discussed. So that I think could be a good evidence for that kind of UD story.
All right, thank you very much. Let's thank Paul again, and thanks to all of the speakers for a great discussion. Note that in the chat here, I again pasted the link to the discussion page for this talk, as well as for the previous talks. You can also find these links on the program page to have continued asynchronous discussion there. This wraps up our first morning session. Thank you all for being here. We're running a little bit behind right now. However, we will get back on schedule. We're all still fresh. We can stomach a 15-minute coffee break. Just get your coffee quick. We will be right back on at 11. For those of you that are presenting in this next session, we are going to shut down the whole webinar and then basically start it right back up. There is no way to stop the broadcast otherwise. So please just sign right back in so we can get ready and prep for the next session. And everybody else, we'll see you back at 11.